If I work through the first one with you guys, free response, and then we'll see if you can do one. Okay. So it actually says problem number 7 is the one we're on. So an astronaut is orbiting space. Craft fires a 0.1 kilogram dart so that it travels in a straight line through point P, and in the vicinity of an axis fixed at point O, the dart's constant speed is 10 miles or meters per second. All right, A says calculate the dart's angular momentum about O at the instant it passes through point P. So they're talking about angular momentum, and you know what formula is for angular momentum? You know what letter it is for angular momentum?
L.
L.
Omega.
Okay, so look at your formula chart, find the L, and it's equal to what? R cross P or I omega. And the one you use depends on what they give you.
This is RXB.
R cross P, kind of a small x. Okay. So this is a cross product. Have you done cross products?
Nope.
Nope. Okay. It actually tells you on the formula chart, not on the one I gave you, but on another piece of paper, that the cross product is sine. Okay. So L is equal to R. P is the linear momentum, which you can replace with mv, and then cross product is sine theta versus the dot product, which is cosine theta. So this is the formula we're going to use. Now, it actually doesn't matter where you find the angular momentum, because the angular momentum is conserved unless there's an external force acting on it, and there's no external forces acting on this dart. Okay, so angular momentum is conserved, so L initial is going to be equal to L final, which means even though they say find it at point P, I'm not going to find it at point P, because then I would have to find this angle and do a bunch of other stuff, right? So I can find it at any point, so I'm going to find it right here. That's the easiest thing to do. So L is equal to R, which is the radius, which is the distance, 0.3. The mass of the dart is 0.1 kilograms. Velocity they told you was 10. And then it's sine of the angle, and this angle at the start point is 90 degrees. And since you're all experts at the unit circle, you know sine of 90 is 1. Good. So it's just 0.3 times 0.1 times 10, which is 0.3. And then the units are mass is kilograms, radius is meters, and velocity is meters per second, so it's meters squared over seconds. So the moral of the story here is find it at the easiest point possible as long as the angular momentum is conserved, okay? Just to show you that that works, rather than find it at point P, let's say theta is equal to 30 degrees. So hopefully you know from your 30, 60, 90 pattern that if this is 30 degrees, it's 0.3, then the hypotenuse is what? Yeah, 0.6, because it's a 30, 60, 90, so if this is 0.3, this is 0.6, and this is 0.3 square roots of 3. That follows that pattern, x square roots of 3, and 2x that your geometry teacher should have taught you a long time ago. And if they didn't, that's okay. So this is 0.6, right? So if I instead replace the 0.3 with a radius of 0.6, and I replace this with sine of 30, what's the sine of 30 degrees? Or the sine of pi over 6? 1/2. And half of 0.6 is 0.3. So it doesn't matter where you find it. So find it at the easiest way possible, which is usually just the perpendicular and the 90-degree one. All right, for part B, the dart passes through P and continues to follow the dashed line. The dart's distance from point O decreases and then increases. How does the dart's angular momentum about point O change as it travels along the dashed line? And I just told you the answer to that. So what happens to the angular momentum? Stays constant. So just check the dart's angular momentum about point O remains constant. And then your reasoning might be the speed, the mass, and r sine theta all remain constant, therefore L remains constant. All right, now point P is on this wheel. That, I guess. So the dart's going to come along, hit that point P. The dart sticks to the tire of the bicycle wheel, causing the wheel to turn on a frictionless bearing with an angular velocity of 1.5 radians per second. So angular velocity is what Greek character? Omega. So omega is 1.5 radians per second. All right, they want you to calculate the rotational inertia of the following. So first, the dart stuck to the wheel. So the rotational inertia, or I, of the dart, and we're just going to treat the dart as if it's a point, so that's just mr squared. And they told you the mass of the dart is 0.1. The radius at point P is 0.5, and you square that. So 0.25 times 0.1 would be 0.025, and this again is I, which is kilograms times meters squared. Because mass is kilograms, radius is in meters, and you square it. All right, then they want you to do the combined dart and wheel system. So the total I is equal to the I of the dart plus the I of the wheel. Now remember, L is equal to RMV sine theta, or it's also equal to I omega. And in this case, which one do I want to use? This one, because they told me this. Okay. So I need the I of the wheel, or actually just the whole combined system on this one. So since I know angular momentum is conserved, Li is equal to Lf. And L initial from part A way back there was 0.3. And LF is going to be I omega for the wheel. This is 0.3, omega was 1.5. And then divide by 1.5. So the I is 0.2 kilograms per, or times meter squared. And this is I total. Then part 3, now find the I of the wheel. So I already know the dart and I know the total, so I can just plug in here. So the total is 0.3 The eye of the dart is 0.025. And then the eye of the wheel is what I'm looking for, so the eye of the wheel is 0.2 minus 0.025, which is 0.175 kilogram meter squared. All right, D, can the wheel be treated as a hoop or a ring of mass? And then you need to know the eye of a hoop. Sometimes on the AP exam, they will give you eye, and sometimes they won't. So you need to know eye for a hoop, a disc, and a sphere would probably be the three that I recommend you memorize. So eye for a hoop is just mr squared. And then the mass is 0.9, they gave you that on the last page, so 0.9 kilograms. And the radius is 0.5 squared. So that gives you an eye of 0.225 kilogram meter squared. And since the eye of the wheel is not the same as this, then no, you cannot model it as a hoop or a ring of mass. And you might want to write these down as ones to memorize. Eye of a hoop is mr squared. Eye of a solid disc is 1/2 mr squared. And eye of a sphere is 2/5, I think.
We learned that.
Yeah, okay, good. Those are the three I would have memorized. All right, for E, how much kinetic energy is lost to other forms of energy when the dart strikes the wheel? So to do that, what two things do I need? Know how much is lost, I need to know what I started with, right, and what I ended up with. So all the kinetic energy initially came from what? Or all the energy came from the dart. So kinetic energy of the dart is 1/2 mv squared, and I'm using that because I know its mass and velocity. So it's 1/2, the mass of the dart was 0.1, its velocity was 10 meters per second squared. So that's 100 times 0.1, or no, 50 times 0.1, which is 5 joules of energy to begin with. And that's the initial two. And then K final, all this translation got changed into rotation, right? So what's the kinetic energy formula for rotation? It's on your chart.
1/2 I omega.
Yes, 1/2 I omega squared. Okay, 1/2, this is the I of the complete system, which is 0.2. And omega was 1.5 radians per second. You gotta square that. Plug that in a calculator, get 0.225 joules. obviously the amount lost is, or lost to other forms is K initial minus K final. So 5 minus 0.225 is 4.775 joules. That was lost. All right, you want to try one? All right, turn to problem 8. We'll go through it step by step.
Gotta do this stuff in Texas too.
What's that?
You gotta do this in Texas.
Yeah.
Like you teach the same class.
Mechanics? Yeah, I teach calculus mechanics and environmental. So, yep, we take the same test you guys do and everything. My school doesn't have the grant with IMSA anymore. We had a 5-year grant. But I still work for them. All right, in this case, rod hanging down off this pivot. And then you have this object that's going to hit the rod at the bottom at 10 meters per second, and this is a 1 kilogram ball. The rod's 3 kilograms, and its length is 1.2 meters. So obviously when it hits the rod, what's going to happen to the rod? Swing up, right? All right, part A, how much potential energy does the bar gain as it becomes horizontal after the collision? So find your formula for potential energy. And there is a little trick on this that you got to think about. See if you can find the change in the potential energy of the rod. Give you a hint, the little trick in here has to do with the height. Alright, for this problem, potential energy is mgh. What mass am I going to use for the rod? 3. Gravity, let's call 10. This is where it's a little tricky. What's the change in height? Not 1.2. Not negative 1.2. When you have a rod like this, squared, you have to consider the mass to be. Is that all right? So what's the change in height? 0.6. 30 times 0.6 is 18 joules of energy. All right, B, determine the angular velocity of the bar immediately after the collision. And because there's no friction in here, because it says it goes freely, all your energy is coming from the ball, which is 18 joules. See if you can find the angular velocity, or omega, using the correct formula. Can determine the right formula to use. That's more than half your battle, probably. And the hint is, since you already found the energy, I would probably use the energy one to find omega. So you're going to use this formula. Energy is 1/2 I omega squared. You already know the energy is 18. You're looking for omega. And what did they tell you about I for this rod? I of the rod is 1/3 ml squared. So I is equal to 1/3 times the mass, which is 3, because this is for the rod. And the length is L, and the L is actually 1.2 squared. So that's 1.44, I believe. Maybe not. 1.4? Okay. Alright, so plug that in here. Solve for omega. So omega is equal to the square root of 18 divided by half of that is 0.72. And that That should give you 5. And what are the units for omega?
Two radians per second.
Good, radians per second. On the next page, for the system consisting of the object and the bar, linear momentum is not conserved in this collision, but kinetic energy is conserved. So kinetic energy is conserved, and K initial equals K final. And then C, determine the speed V of the 1 kilogram object immediately after the collision. So all the kinetic energy initially comes from what? The ball that hits the rod. So find that kinetic energy of that. And then kinetic energy final is going to include what 2 things? The rod and the ball after the collision. So you got to add those 2 things together to get the final kinetic energy. And then you're solving for the final speed of the ball just after the collision. So for the kinetic energy of the ball, which formula are you going to use? 1/2 mv squared or 1/2 I omega squared? 1/2 mv squared. That's initial for the ball. Alright, for the kinetic energy final of the rod, what are you going to use? Which kinetic energy formula? Yes, 1/2 I omega squared. Or there's another way you can kind of do that one because you already have it. And then final kinetic energy of the ball is going to be what? Which formula? Ball have a velocity or does it have an angular velocity? It's the velocity, so you're back to 1/2 mv squared final for the ball. Plug all your numbers in and find the final velocity of the ball right after the collision. 1/2, what's the mass of the ball? 1. What's the initial velocity of the ball? 10 squared equals, now this, that's the energy, right, in the rod, which I already calculated as what? 18 joules. When I did the potential energy, so this is 18 joules. Plus 1/2, mass of the ball again is 1, and V final squared is what I'm looking for. So this is half of 100 or 50. Subtract 18, gives me the 32. Multiply by 2, that's 64. It's V final squared, so V final is square root of 64, 8 meters per second. All right, in part D, calculate the following values of angular momentum about the axis of the bar. So this is like the first problem that I did with the dart. So part 1, find the angular momentum of the object immediately before the collision. So see if you can do that. Find the angular momentum of the object immediately before the collision. Kind of like energy, you gotta decide which one to use. Same thing here. So for the ball, which one do I use? Does the ball have a velocity or an angular velocity? It's got a velocity, right? So you use this one. So L is equal to R, which is what? 1.2. That's the radius, which is the length of the rod, 1.2, times the mass, which is 1, times the velocity, which is 10, times sine of the angle, which is 90 degrees. Okay.
That's 1, huh?
So that is 1, yes. 12. And mass is kilograms. This is meters, and this is meters per second. So the units are kilogram meters squared over seconds for angular momentum. And it doesn't have a special unit like some of the other stuff does. Remember, as long as there's no external forces on this, so no friction or anything like this, it doesn't matter where you find it. So you'd want to find it at 90 degrees anyway, even though that's right before the collision, like they told you to do. Alright, part two, find the angular momentum of the bar immediately after the collision. So for the bar, think about which formula you're gonna use. And you are gonna use some of the answers we've already gotten previously to plug in. Alright, bar has what kind of momentum? Or you're gonna use this one, right? Because it's got a omega to it, so. L the bar is I omega, you know, I is 1/3 mr squared times omega, or the 1/3 mr squared, I think we already might have had, but 1/3 times 3 times 1.2 squared, and omega was the 5 that we got previously. So we should have gotten 7.2 kilogram meter squared per second. So, even though this is moving in a straight line, right, and it has a linear momentum, about a point that's away from it, it also has an angular momentum, even if it's not rotating. Does that make sense? So, at least for that second, it's got that angular momentum along it. Obviously, when it's rotating, then you also have the angular momentum. That's a little bit more obvious. All right, determine the angle theta. So if you have this L is 12 initially, right? And then this much went into the bar, then you still have some L left for the ball, right? So basically that's what you're using is for the L of the ball after the collision. That's what you're trying to find. Or you're gonna, you know what that is because it's this minus this, so that's 4.8. And then since it wants the angle, again, which formula are you gonna use? The one with the angle in it, right? So set 4.8 equal to R mv sine theta and solve for the angle. And remember, this is after the collision, so you're gonna use the numbers for after the collision. while I'm thinking about it, in your calculators, and when you're doing degrees or angles in calculus, your calculator is always in what mode?
Degree.
In calculus, you're always in radians, never in degrees.
Okay.
In physics, you can change back and forth, but usually physics is in degrees. So, but in calculus, if it's an angle, you're always in radians, always, always, always. All right, what R am I going to use? Immediately after the collision? 1.2. Mass is still 1. V is 8. That was from part C up above. That's 9.6. So divide by 9.6. 48 over 96 is a half. And then you do the inverse sign of a half, which is, or where on the unit circle is sign equal to a half.
5 or 6.
5 or 6 or 30 degrees. Actually, hold on. Let me look at that picture again. Yep. The way they drew the picture, so the ball comes this way and then heads this way. This 30 degrees is actually right here, and they put theta right there, which means it's actually 60 degrees. So the angle they were looking for is actually 60 degrees. All right, part F, briefly explain why linear momentum is not conserved during this collision, but why angular momentum about the axis is conserved. So, momentum is conserved as long as there's not what? An external force, right? So, even though this thing swings freely, there's still a force here that's going to hold this rod on. So there is an external force acting on it, which changes the momentum of the system. The force does not exert a torque because it's along the axis, so angular momentum does not change. And that's on your formula chart. Doesn't look like it is on your formula chart. This is another formula that I have my kids memorize. Is torque is equal to the change in linear momentum over change in time. So if the torque is equal to 0, the derivative of what gives you 0? Always.
Any number?
A constant, right? So if the torque is 0, that tells you that the change in the momentum is constant, or the angular momentum is constant. So if that's true, then dl dt is a constant. All right, turn over to problem number 9. Nine starts with 2 balls heading towards each other on frictionless ice, or actually it's 2 hockey pucks. One's initially at rest. I give you the speed before the collision. After the collision, M moves to the left with a speed of 3 meters per second. They want you to find the final speed of puck M. See if you can determine that.
This time we'll go ahead and announce our next winners. Any winners can report to the live oak table in the middle hallway. Travis Rosenberg, Victoria Bowler, Jared Graffia, Nathan Long, Taylor DeVille, Peyton Mitchell, Cameron Myers, Cade McKinnis, Cameron Summerall, Joshua Skyner, James Damari, Lindsay Rizzo, Ashley Guillory, and Patrick Holwanger. At this time, you can report to your next rotation.
So this is linear momentum, so MVI plus big MVI equals MVF plus big MVF. So mass is 2, velocity is 9, this is 0 because it's not moving. Mass is 2, the velocity is what? Negative 3, because it's going in the other direction, plus mass is 12, B final is what you're solving for. 18 plus 6 is 24, divide by 12, B final is 2 meters per second. All right, take a little break. One more to go.